Welcome to MEI Modelling with Algorithms. We're on the topic Linear Programming 3, Application to Network Problems, and this is video 3.2, Longest Path Problems. So here's an example of a very simple network. You'll recognize this from the previous video when we were looking at the shortest path problem. This time we want to find the longest path from A to D, and what I'd like you to do is just have a think as to what sort of problem that we've met so far in this course we might apply this to. When might we want to find the longest path? Now we can formulate this as a linear programming problem in a very similar way to what we did with the shortest path. So we're going to need 6 variables, one for each arc and direction that we can realistically imagine needing. So the arcs that leave A and the arcs that arrive at D could only ever be traversed one way, but this arc BC or CB might be reversed in either of those two directions. That makes a total of 6 variables, and they can only take values of 0 or 1. In other words, they are either included in the path or they are not. So really the only difference with longest path is that we're dealing with a maximization problem. So our objective function is the same as before. We create it by multiplying the weight of each arc by the variable that we're associating with that arc. So when I write 2ab, that's either 2 times 1 or 2 times 0, depending on whether AB is included or not. And then we have 4AC and so on, like that. So now let's think about the constraints. So firstly, we can only leave A once by one arc, so either AB is 1 or AC is 1, and that's the only possibility. So if I add AB and AC together, I'll get 1, because if one of them's 1, the other one has to be 0. So I can say AB plus AC equals 1. Now we can only enter and leave B once, and also as we enter B by one arc we must leave by another. So if I add together the two arcs, the two variables corresponding to the arcs which lead into B, so that's AB and CB, at most one of those will be 1, and if one of them is 1, then one of the arcs which is leaving B will also have variable associated with it of 1. So if I subtract those ones, B, C and B, D, that must give me 0. Alright, now I can say a similar thing about node C, so I'll write that down. So the arcs entering C, so that's AC and BC, and then subtract the arcs which are leaving C, so that is CB and CD, that must equal 0. And finally, because we had to arrive at D in the end, by one of those two arcs, BD or CD, we know that BD plus CD must equal 1. So this is the formulation of our problem. So we've got this objective function here, and we've got these constraints, and we have the additional constraint that the variables must be either 1 or 0. Now it's more important with longest path problem than with shortest path to really insist that these values are binary, because with the shortest path, because it's being minimized, they would actually end up being either 1 or 0 anyway, as long as they were integers. But with longest path, if you don't make that restriction, then your solver is going to try to make them larger than than 1. So it really is important. Now, if your solver doesn't have a binary option, and some of them don't, it will have to have an integer option, otherwise it won't work at all. But if it has an integer option but no binary option, then what you can do is introduce these extra constraints. So for each variable, as well as it being an integer, say that it has to be less than or equal to 1, and then that will do the trick. Now, if you remember the video about the linear programming solver that you can add into Excel, this is what it will look like once we've put our linear programming problem for the longest path into it. So here we have the names that were given to these variables and their initial values, which are always 0, whatever the linear programming problem is that we're doing in this way, and then we have the coefficients of those variables that form our objective function, and then we also have the constraints that we talked about in the previous slide as well. Alright, now once we've set that up, we can click solve and we will get this report, and again we just need to make sure that we can interpret this correctly. We can see that we've got a length of our longest path of 9, and the variables tell us whether or not these arcs are included. So if we look at the final values of those variables, we can see that the arcs which it's chosen to include are BD, because that's got a 1, AC and CB. Now, I asked you to think earlier about why this might be used. Hopefully you realised that when we're doing critical path analysis, that's exactly what we are doing when we're finding the critical path. Because all of these activities have to be done, it's going to be the longest path through that will give us the minimum time for the whole process to be completed. Now, we're not going to do this problem in full. I just want you to think about the following question. How many variables are going to be needed in this problem that you can see there? So pause your video and have a think about that, and also think about what the constraints might be. Okay, so if you think you've got an answer to that, you can compare it now with this. This is the formulation of the problem as it would be done in Lindo. So we can see here that the objective function that you'll need is that. So see if that corresponds with what you wrote. And these are the constraints. Obviously, because this is all these things are directed anyway, we don't ever have any which are going in both directions. And of course, these all need to be integers, so you must include an end and then integers for each of these. It's worth pointing out that earlier we had the word GIN, now I've got INT. That is a Lindo thing. So GIN is an integer as we understand it, and in Lindo INT is strictly binary. Alright, so really what they're saying there is these things are binary. Bit confusing that, but that's just the way Lindo is. Alright, and then the output that it will give is this. So it's found a longest path of 12, and we can see on here that the arcs it's chosen to include are AC, CD, DE and EF. So we can actually draw that on here if we want to as well. So we're going from A to C, and then C to D, D to E, E to F. And so it's found our critical path for us there. So that concludes video 3.2, longest path problems. The final video in this topic is going to be 3.3, network flow problems.